So this video is about dating the age of the Earth, and I hope it complements the Cosmos video that I posted on Canvas. So we know that the age of the Earth is 4.54 plus or minus 0.05 billion years old. Well, how did we come to get that number? Well, we used radioactive isotopes and primarily uranium-238. We know that uranium-238, its half-life is 4.5 times 10 to the 9 years. And so that makes it a good tool given the sample that we're trying to date. That is a good half-life for something as old as the Earth. And so we also know that the decay of uranium-238 is a series. There's multiple steps along the way, but we know that the first step, the slow step, is the rate determining step. And so the way we're going to approach dating the Earth is by looking at the ratios of uranium-238 and lead-206. Lead-206 is the stable isotope that's formed at the end of the series. But we need to involve other isotopes in order to find the age of the Earth. And so here's the series for uranium-238. We covered this in a previous video where uranium-238 goes through different alpha and beta decays and ends in lead-206. And again, we have the different half-lives for the different nuclides within the series, but the first half-life is the slow step. So when we look at the ratio of uranium-238 to lead-206, we need to consider that, well, at the beginning of the formation of the Earth, there was already lead-206 present. And then over time, uranium-238 has decayed into lead-206. So we need some way to figure out how much lead was there at the beginning and how much of that was natural from the formation of the Earth and not from the decay of uranium. Well, what we do is we need to also monitor lead-204. That is really the only lead isotope that's non-radiogenic, meaning whatever lead-204 is on Earth now was here during the beginning. It is not a part of a decay series. Lead-208 is the endpoint for thorium-232. Lead-207 is the endpoint of the uranium-235 decay series. So these isotopes have changed over time. But again, lead-204 has not changed. So in order to determine the age of the Earth, we need a sample from that had the original isotopic ratio of when the Earth formed. That we need. We need N naught. And then we also need a sample of the Earth as it is today. And so what Claire Patterson did was he used a meteorite from Diablo Canyon crater. This meteor was very special in that it contained very high content of sulfide. And so now we're dealing with some chemistry here. The fact that this meteor had such a high sulfide content is a chemist knows that this is somewhere that you can find a high amount of lead and essentially no uranium. Uranium does not like to bind with sulfur. Uranium primarily forms oxide minerals. So in a meteorite that has a lot of oxide minerals like iron oxide, aluminum oxide, that's where you're going to find uranium. But lead, it prefers sulfide. And if you're a chemist, this kind of follows hard, soft, acid, base theory. And so this meteor, because there was no uranium in it, it gave a very good estimate of the natural lead isotopes, the ratios of lead-204 to lead-206 and so on, of the Earth when it formed. So that's our one sample. We now know the lead ratios at the beginning of the solar system formation or when the Earth formed. So this figure just shows uranium speciation in nature. So we have speciation versus pH, and all is meant by speciation is what form is the uranium in at different pHs. And again, what we see in nature is that uranium likes to be with oxygen. And so in the Diablo Crater Canyon meteorite, high in sulfide, we are pretty confident that none of that lead-206 was due to the decay of uranium, because we will not find uranium in a high sulfide environment. So on Canvas, I've also attached the original paper authored by Claire Patterson, which discusses dating the meteorites and the age of the Earth. He used this relationship, which we won't do calculations, but you do see that it incorporates the non-radiogenic lead-204, which again has not changed over time, since the formation of the Earth, and lead-206, which some of it could be from the beginning, meaning it had always been here, but other parts of it could be due to uranium-238 decay. So what Claire also used was zircons. Now these zircons, they have oxide minerals and they contain uranium-238. And so these zircons are like little time capsules because they've survived erosion, they've survived high pressures and temperatures. They're very refractory type of material. And so they've preserved the uranium-238 at the start. So these zircons are going to give us N. They're going to be able to tell us, we have N naught from the meteorite. The zircons are going to allow us to see how the uranium has decayed into lead and allow us to date the Earth. So with this information, I want you to watch the Cosmos video. Again, this is to complement what the video discusses. And also, what I want you to get from the Cosmos video is how fundamental research on determining the age of the Earth, how that can lead to changing society in ways that we have no idea when we're actually doing the research. So it's a great story, and I hope you watch the Cosmos video.